Picture this: a night so vast and silent, stars scattered like distant fireflies, when suddenly two galaxies hurtle toward each other in the darkness. Their dance is violent, beautiful, inevitable. Stars are wrenched from their orbits, gas clouds ignite in brilliant bursts, and the fabric of space itself trembles. This isn't science fiction, it's how our universe works. Cosmic collisions, cataclysmic, chaotic, and utterly breathtaking, are the architects of everything we see. From the birth of galaxies to the forging of planets like our own, these titanic crashes have shaped reality itself. And today, we're diving deep into 25 of the most extraordinary collisions ever witnessed or pieced together by science, each one a turning point in the story of the cosmos. Think about the ground beneath your feet, the air in your lungs, even the device in your hands right now. Every atom, every element heavier than helium, was born in the heart of a stellar explosion or the crushing embrace of colliding neutron stars. The gold in your jewelry, the iron in your blood, they didn't exist until stars lived, died, and slammed into each other in spectacular fashion. These collisions aren't just destructive, they're creative forces sculpting the universe with a violence so profound it gives rise to new worlds. And the wildest part, they're still happening. Right now, as you watch this, galaxies are merging, black holes are spiraling toward each other, and somewhere out there, a collision we can't yet see is brewing, one that might rewrite the cosmic map all over again. So buckle up, we're about to journey across billions of years, from the universe's fiery infancy to its uncertain future, through collisions that defied imagination. Some of these events were so powerful they bent space-time itself. Others left behind scars we can still see etched into the night sky. And while we might feel small under these endless stars, remember, we're made of the very stuff these collisions forged. This is the story of how chaos creates, how destruction builds, and how the universe in all its violence crafted a home for us. Let's begin. At the very beginning, before stars, before galaxies, before even time as we know it, there was a collision so colossal it birthed the universe itself. The Big Bang wasn't just an explosion in empty space. It was the ultimate cosmic collision, a moment when all matter, energy, and even the laws of physics roared into existence in an unfathomable instant. Picture it like two cosmic titans slamming together with such force that reality fractured and expanded, setting the stage for everything that would ever exist. But what could have collided to create everything? Scientists have spent decades untangling this mystery, and some theories sound like they're straight out of a sci-fi epic. Take brain cosmology, for example. Imagine our universe as a single page in an infinite cosmic book, a brain floating in higher dimensional space. What if another brain, another universe, smashed into ours? That collision could have unleashed the energy of the Big Bang, igniting the expansion we're still riding today. Then there's the quantum foam hypothesis. At scales smaller than atoms, space itself might not be smooth but frothing with tiny, chaotic fluctuations like a bubbling cosmic sea. If two of these quantum bubbles collided just right, their energy could have tipped the scales, triggering the birth of our universe. Here's the wild part: we're still seeing echoes of that primordial collision. The cosmic microwave background, the faint afterglow of the Big Bang, is like a photograph of the universe's first moments, its subtle ripples revealing where matter clumped together to form galaxies. And every element in your body, from the oxygen you breathe to the calcium in your bones, was forged in the aftermath of that collision, as the universe cooled and particles fused for the first time. The Big Bang wasn't just an event. It was the first domino in a chain reaction of cosmic violence, a collision so profound it set the rules for every crash, merger, and explosion that would follow. Without it, there'd be no stars, no planets, no us. And yet, even now, we're still uncovering its secrets, proof that the universe's greatest story began with the mother of all collisions. The universe was almost nothing, a flash of light, a blink of existence erased before it could begin. In the first fractions of a second after the Big Bang, matter and antimatter waged the ultimate cosmic war. For every particle of matter born, an equal and opposite particle of antimatter flickered into being, and when they met, they annihilated each other in bursts of pure energy. It should have been a perfect stalemate, a universe that flickered out as quickly as it began. But something tipped the scales. Out of every billion collisions, one particle of matter survived. And that tiny imbalance, that cosmic oversight, is why you and I exist today. Scientists call this mystery baryon asymmetry, and it's one of the greatest puzzles in physics. Why wasn't the annihilation total? Why did matter win? At CERN, physicists are smashing particles together at near light speed, recreating those primordial conditions. And they've found clues in the behavior of quarks, the building blocks of protons and neutrons. Some particles decay slightly differently than their antimatter counterparts, like a cosmic coin that lands on heads just a fraction more often than tails. Over time, those tiny biases added up, leaving behind just enough matter to build galaxies, stars, and us. But here's the real twist: if antimatter had won, the universe would look identical. Anti-stars, anti-planets, maybe even anti-life, all obeying the same laws of physics, just built from mirror-image particles. The fact that we're here, made of matter, might just be a roll of the dice on a universal scale. And this collision's legacy is everywhere. Every atom in your body is a survivor of that ancient annihilation, a descendant of the 1 in a billion that outlasted the chaos. Without that imbalance, the universe would be nothing but an endless sea of light, no planets, no chemistry, no life. So the next time you look up at the night sky, remember, you're staring at the aftermath of the universe's first and greatest near miss. For billions of years after the Big Bang, the universe was dark, a silent, featureless expanse of hydrogen and helium gas. No stars, no light, just an endless cosmic fog. Then something extraordinary happened. The first stars ignited, tearing through the darkness like beacons of creation. But these weren't just any stars. They were monsters, colossal, short-lived, and forged in the violent collisions of dark matter halos, the invisible scaffolding of the early universe. Dark matter, mysterious, invisible, and outweighing normal matter 5-to-1, was the universe's secret architect. As gravity pulled its filaments together, halos of dark matter smashed into each other, creating deep gravitational wells where ordinary gas could pool. These collisions were the cosmic nurseries where the first stars, known as population Roman 3, were born. And they were unlike anything we see today. Imagine stars hundreds of times more massive than our Sun, blazing at temperatures so extreme they fused hydrogen into heavier elements in mere millions of years, a blink in cosmic time. Then came the explosions. When these giants died, they didn't fade quietly. They detonated as supernovae so powerful they ripped apart the very fabric of their surroundings, seeding the cosmos with the first heavy elements. Recent discoveries from the James Webb Space Telescope have given us tantalizing glimpses of these ancient fireworks. In distant galaxies, astronomers have spotted unusual chemical signatures, helium-rich gas, and a puzzling absence of heavier metals, hinting at the aftermath of population Roman 3 star collisions. But the real shock: some of these primordial stars might not have died in supernova at all. Theories suggest the most massive ones could have collapsed directly into black holes, vanishing without a trace and leaving behind gravitational echoes we're only now learning to detect. Every time we peer deeper into the cosmos, we're essentially looking back at the wreckage of these first cosmic collisions, the explosions that set the stage for everything to come. Without them, the universe would still be a sea of featureless gas, no planets, no life, just darkness. Those first monstrous stars didn't just live violently, they died in explosions that reshaped the cosmos. When a population Roman 3 star reached the end of its brief, fiery life, it didn't fade away. It detonated with a force so unimaginable that for a few blinding moments, a single star could outshine an entire galaxy. These weren't just deaths, they were cosmic alchemy labs forging elements heavier than hydrogen and helium for the very first time. In the heart of these supernovae, temperatures soared to billions of degrees, smashing atoms together so fiercely that they created carbon, oxygen, and even iron, the building blocks of planets and life itself. Take the Crab Nebula, a sprawling remnant nearly 1,000 years old. When astronomers peer into its swirling gases, they're looking at the aftermath of a supernova recorded by Chinese astronomers in the year 1054. But here's what makes it special. Embedded in its core is a pulsar, a rapidly spinning neutron star, the dense corpse left behind by the explosion. This pulsar acts like a cosmic lighthouse, blasting beams of radiation as it rotates 30 times every second. And the nebula's glowing filaments, they're laced with sulfur, oxygen, and neon elements cooked up in the star's final moments and then hurled into space at millions of miles per hour. What's staggering is that this same process, repeated billions of times across the early universe, turned an empty cosmos into a chemical playground. Supernova didn't just scatter heavy elements, they created shock waves that compressed nearby gas clouds, triggering the birth of new stars with richer chemistry. Over time, these later generation stars would go on to form planets, asteroids, and eventually, the raw materials for life. Modern telescopes like the Hubble and Chandra X-ray Observatory have given us front-row seats to these stellar fireworks. In distant galaxies, we've spotted supernovae so bright they outshine their host galaxies for weeks, each one a fleeting glimpse of the same processes that enriched our own corner of the universe. And when scientists analyze the light from these explosions, they find fingerprints of calcium, titanium, and gold, proof that the jewelry on your wrist or the fillings in your teeth were forged in the hearts of dying stars. But the true legacy of these first supernovae is written in your DNA. The phosphorus in your bones, the iron in your blood, even the zinc that helps your immune system, all of it was once stardust blasted across space by these ancient collisions. Every time you take a breath, you're inhaling oxygen atoms that spent billions of years drifting through the void before becoming part of you. The universe didn't just create life, it recycled itself into life, one cataclysmic explosion at a time. And the wildest part, this process is still happening. Right now, somewhere in the cosmos, a massive star is reaching the end of its life. When it explodes, it'll seed another corner of the galaxy with the ingredients for future worlds, and maybe, just maybe, for life we'll never live to see. The Crab Nebula is a gravestone, but it's also a blueprint, a reminder that destruction and creation are two sides of the same cosmic coin. The Milky Way didn't spring into existence fully formed. It grew through a relentless series of cosmic crashes, a chaotic construction project spanning billions of years. Picture a puzzle where each piece is an entire galaxy, smashing together in slow motion until they merged into the glittering spiral we call home. Thanks to groundbreaking data from the Gaia spacecraft, we now know these collisions left behind invisible scars, rivers of stars, known as stellar streams, weaving through our galaxy like celestial breadcrumbs leading back to its violent past. One of the most dramatic mergers happened roughly 10 billion years ago, when a galaxy now called Gaia Enceladus, at least a quarter the size of the young Milky Way, slammed into it head-on. The impact was catastrophic. Stars were torn from their orbits, flung into chaotic new paths, while vast clouds of gas collided and ignited new waves of star formation. Gaia's precise stellar maps reveal survivors from this collision. Stars moving backward compared to the Milky Way's rotation, their chemical signatures betraying their foreign origins. Then there's the Helmy Stream, a group of stars orbiting at a steep angle to the galactic disk. These are the stragglers of another ancient merger, a smaller galaxy shredded by the Milky Way's gravity, its stars scattered like confetti. Even our galaxy's iconic spiral arms might owe their existence to these collisions. Computer simulations show mergers can trigger density waves that compress gas, lighting up new generations of stars in swirling patterns. But the most haunting relic might be the Sagittarius dwarf galaxy. Right now, it's in the process of being devoured. Over the past 6 billion years, the Milky Way's gravity has stretched it into a looping ribbon of stars wrapping around our galaxy, a real-time snapshot of galactic cannibalism. Gaia has spotted entire star clusters within this stream, their movements betraying the slow, inevitable pull of the collision. These mergers aren't just history, they're still shaping us. The gas and stars they delivered built the Milky Way's disk and enriched it with heavy elements. Even our solar system might exist because of them. Some theories suggest the compression waves from mergers triggered the collapse of the gas cloud that became our sun. Every time you gaze at the night sky, you're seeing the aftermath of these titanic collisions, the glowing wreckage of 100 galaxies fused into one. And the Milky Way isn't done. In about 4 billion years, it will collide with the Andromeda Galaxy in a merger so massive it will redefine both forever. But that's a story for another collision. 4.5 billion years ago, before the Moon cast its silver light over Earth's oceans, our planet was a very different place, a roiling, molten world under relentless bombardment. Then came the crash that changed everything. A Mars-sized object named Theia, born from the same cosmic nursery as Earth, was hurtling toward us at over 15,000 miles per hour. When it struck, the impact was so violent it nearly shattered both worlds. Molten rock sprayed into space, Earth's crust was vaporized, and for a brief, apocalyptic moment, our planet wore a glowing ring of debris like a halo of fire. This is the giant impact hypothesis, and it explains why the Moon isn't just a captured wanderer, it's a piece of Earth itself. Recent studies of Apollo moon rocks revealed something astonishing. The isotopic signatures of oxygen in lunar samples match Earth's almost perfectly. That's the cosmic fingerprint proving Theia didn't just graze us, it merged with us, its material blending with Earth's mantle before the ejected debris coalesced into the Moon. But the collision did more than give us a celestial companion. Theia's glancing blow knocked Earth off kilter, leaving our planet tilted at 23.5 degrees, the reason we have seasons. Without that tilt, Earth's climate would be monotonous, with no winter snows or summer blooms to drive the diversity of life. The impact also supercharged Earth's rotation, giving us days that lasted just 5 hours until the newborn Moon's gravity gradually slowed us down to the 24-hour rhythm we know today. Here's where it gets even wilder. Some scientists now think Theia's remnants didn't just vanish. Deep beneath our feet, 2 continent-sized blobs of dense material, one under Africa, the other the Pacific, could be the shattered remains of Theia's core, slowly sinking through Earth's mantle over billions of years. These subterranean mountains might still influence volcanic activity today, meaning Theia didn't just give us the Moon, it might be shaping earthquakes and eruptions under our feet. The legacy of this collision surrounds you. Without the Moon's steadying pull, Earth would wobble chaotically, flipping climates between extremes. No lunar tides means shallow coastal waters, no intertidal zones, perhaps no leap for life from sea to land. Even our cultural myths, our calendars, our very concept of time stem from that cataclysm. Every time you see the Moon hanging in the sky, you're looking at a relic of the day Earth was remade, a cosmic accident that turned our planet into a haven for life. The early solar system wasn't the orderly place we see today. It was a shooting gallery with planets jostling for position and asteroids careening like rogue bullets. Then came the late heavy bombardment, a 400-million-year reign of terror where the inner planets were pummeled by an avalanche of asteroids and comets. But this wasn't random chaos. Behind the violence stood Jupiter, the solar system's gravitational bully, whose migration triggered a collision cascade that reshaped everything. Here's how it happened. In the solar system's infancy, Jupiter likely formed much closer to the Sun before drifting inward, then outward, a movement known as the Grand Tack. As it plowed through the asteroid belt, its immense gravity flung debris in all directions. Some rocks spiraled toward the sun, while others were ejected entirely. But countless more became projectiles aimed squarely at Mars, Earth, Venus, and the Moon. The evidence is etched into lunar craters like Tycho and Copernicus gaping scars that tell us this bombardment peaked around 3.9 billion years ago. But these collisions weren't just destructive. They were delivery trucks, comets packed with ice, slammed into Earth, vaporizing on impact and releasing torrents of water vapor into the atmosphere. Asteroids rich in carbon and organic molecules might have seeded the planet with the building blocks of life. Without Jupiter's gravitational nudge, Earth could have remained a barren desert devoid of oceans. The Moon, lacking erosion or plate tectonics, preserves this history perfectly. Its highlands are littered with craters dating back to the bombardment, while its smoother maria, the dark patches we see from Earth, are lava flows that filled basins created by the largest impacts. When Apollo astronauts brought back lunar rocks, scientists found shocked minerals and glass beads, telltale signs of violent collisions. Even Mars bears the scars. Its southern hemisphere is a pockmarked wasteland, while the north is oddly smooth, a dichotomy some attribute to a colossal impact during this period. And Mercury, its entire surface appears to have been resurfaced by the bombardment, leaving it a cratered relic of the solar system's most violent era. Jupiter's role in this chaos reveals a startling truth. The giant planets are cosmic architects, capable of making or breaking the conditions for life with their gravitational whims. Without that bombardment, Earth might never have gained its oceans or the ingredients for life itself. The next time you sip a glass of water, remember, some of those molecules might have hitched a ride on a comet that survived Jupiter's demolition derby 4 billion years ago. 66 million years ago, the skies over what we now call Mexico were calm, until a mountain-sized rock, traveling faster than a rifle bullet, tore through the atmosphere in a blaze of fire. The Chicxulub impactor, an asteroid nearly 9 miles wide, struck with the force of 10 billion atomic bombs, instantly vaporizing everything within hundreds of miles. But the real devastation came in the hours, days, and months that followed. Tsunamis taller than skyscrapers radiated outward, superheated debris rained back down, and the sky itself turned black as soot and sulfur choked out the sun for years. This wasn't just an extinction event, it was a planetary reset button, one that cleared the stage for mammals and eventually for us. Recent drilling into the Chicxulub crater's peak ring, a circle of mountains formed by the rebound of Earth's crust, has revealed chilling details. The rocks show evidence of temperatures hotter than the sun's surface, pressures exceeding 1,000,000 times our atmosphere, and even fragments of the asteroid itself melted into the impact zone. But the most telling clues come from microscopic glass beads called tektites, found as far away as New Zealand. These were once droplets of molten rock flung into space by the impact, which then solidified and fell back to Earth like deadly rain. The aftermath was a slow-motion apocalypse, with sunlight-blocked global temperatures plummeted by as much as 50 degrees Fahrenheit. Photosynthesis ground to a halt, collapsing food chains from the bottom up. Acid rain poisoned the oceans, while wildfires, ignited by the asteroid's heat pulse, raged across continents. In the fossil record, the Cretaceous-Paleogene boundary is marked by a thin layer of iridium, a metal rare on Earth but common in asteroids, and beneath it, dinosaur bones. Above it, silence, yet this catastrophe was also a catalyst. Small, burrowing mammals, nocturnal, resourceful, and able to survive on seeds and insects, endured where giants perished. With dinosaurs gone, these survivors diversified explosively, filling empty ecological niches. Within 10 million years, the stage was set for primates and ultimately humans. The Chicxulub impact didn't just end an era. It rewrote the rules of life on Earth. Every bird you see today is a descendant of the few dinosaurs that survived, while every human owes their existence to those scrappy mammals that outlasted the darkness. It's a humbling reminder, sometimes the universe's most destructive collisions are also its most creative. The Theia collision reshaped Earth, but what if it wasn't alone? Scientists examining the Moon's composition have stumbled upon a puzzle. Some lunar rocks carry chemical signatures that don't quite match Earth or Theia, hinting at another colossal impactor, one we've yet to name. This controversial Big Splash theory suggests Earth endured two planet-shattering collisions in its infancy, each contributing to the chaos that made our world unique. The clues lie buried deep in Earth's mantle. Seismic scans reveal two continent-sized anomalies, one beneath Africa, the other under the Pacific, where seismic waves slow dramatically. These blobs, each nearly 100 times taller than Mount Everest, are denser and hotter than the surrounding mantle. While some researchers argue they're remnants of Theia's iron-rich core, others propose they're evidence of a second impactor, one that struck Earth at a different angle or even merged with Theia before hitting us. Here's where it gets fascinating. If Earth was hit twice, it could explain why our planet has such a strong magnetic field. The first impact might have tilted Earth's axis and given us the Moon, while the second could have supercharged our molten core's churning motion, the dynamo that generates our protective magnetic shield. Without that second collision, solar winds might have stripped away Earth's atmosphere, leaving us as barren as Mars. The Moon itself holds tantalizing hints. While most lunar samples align with Earth's oxygen isotopes, a few like those from the far side South Pole Aitken Basin deviate slightly. Could these be fragments of a second impactor? Computer simulations show that a follow-up collision, occurring just a few million years after Theia, might have mixed debris in ways that match these anomalies. Yet the implications go beyond geology. If Earth was struck twice, it means our planet's path to habitability was even more improbable. Two planet-sized impacts in quick succession should have sterilized Earth, boiling away oceans and rendering the surface molten for millennia. That life emerged at all suggests these collisions weren't just destructive, they were transformative, setting off chain reactions of volcanic outgassing and climate stabilization that eventually allowed oceans and continents to form. The debate rages on, with skeptics pointing out that a single, messy Theia impact could explain both the Moon's chemistry and Earth's blobs. But one thing's certain, whether it was one crash or two, Earth's early violence didn't just shape our world, it made life possible. Every earthquake, every volcanic eruption, even the air we breathe might trace back to these cataclysmic moments when alien worlds merged with ours, rewriting the rules of planetary survival. Right now, across the unfathomable gulf of space, an unstoppable force is hurtling toward us at 250,000 miles per hour. The Andromeda Galaxy, a spiral giant twice the size of our Milky Way, locked in a gravitational embrace that will end in the most spectacular collision our local universe has ever seen. But don't panic, this cosmic car crash won't happen for another 4.5 billion years. When it does, the night sky will transform into something unrecognizable, a pyrotechnic display of creation and destruction playing out over millions of years. Simulations from NASA, Hubble, and sophisticated computer models reveal a dance both violent and strangely graceful. Unlike the chaotic debris of planetary impacts, galaxies are mostly empty space. When Andromeda and the Milky Way meet, their stars will pass right through each other like ghosts, their vast distances making direct collisions vanishingly rare. But the gas clouds between those stars, that's where the fireworks begin. These colossal hydrogen reservoirs, each billions of times more massive than our Sun, will slam together, compressing under unimaginable pressure. The shockwaves will ignite chain reactions of star formation, lighting up the merging galaxies with blue-hot newborn stars in bursts so intense they'll outshine entire constellations. For Earth's distant descendants, if any still remain, the view will be surreal. As Andromeda approaches, it will swell from a faint smudge in the sky to a glowing disk rivaling the full moon. Over millennia, tidal forces will warp both galaxies, stretching them into grotesque shapes as gravity pulls streamers of stars into long, shimmering arcs. The Milky Way's neat spiral arms will dissolve into chaos, its orderly rotation replaced by a turbulent stellar whirlpool. Then comes the moment of first contact, though collision is almost too crude a word. There's no single crash, just a slow morning merger as gravity weaves the two galaxies together over hundreds of millions of years. Central to this cosmic ballet are the supermassive black holes at both galaxies' hearts. Currently, Andromeda's black hole weighs a staggering 140 million solar masses, while our own Sagittarius, a star, is a relative lightweight at 4 million. As the galaxies merge, these monsters will spiral toward each other, their orbits tightening until they finally collide in an eruption of gravitational waves that will ripple across the cosmos. The aftermath, a brand new galaxy dubbed Milky by astronomers, an elliptical behemoth where the mixed stars of both predecessors orbit in a vast glowing haze. The violence of the merger will likely kick our solar system out to the galactic suburbs, flinging us thousands of light years from the bustling core. Yet even then, the night sky won't go dark. The collision's legacy will be written in new star clusters, planetary nebulae, and perhaps even fresh worlds born from the chaos. Here's the ultimate irony. This collision, which sounds like an ending, is really just another step in the universe's cycle of reinvention. Galaxies grow by devouring each other, and Milky might one day merge with the Triangulum galaxy or others in our local group. The universe builds by breaking, creates by colliding, and rewrites its own rules with every cataclysm. So while the Milky Way as we know it is doomed, its atoms, the same ones in you and me, will live on, recycled into whatever comes next. Imagine two galaxy clusters, each a sprawling metropolis of hundreds of galaxies plowing into each other at unfathomable speeds. This isn't just a collision. It's a cosmic courtroom where dark matter, the universe's most elusive suspect, was finally caught red-handed. Meet the Bullet Cluster, a pair of galaxy clusters officially known as 1E057-7206 and 1E057-7242. Their smash-up, observed by the Chandra X-ray Observatory and Hubble, didn't just send shockwaves through space, it shattered our understanding of reality itself. Here's what happened. When these clusters collided, their galaxies, made of ordinary matter, sailed past each other like swarms of ghostly ships, their vast distances preventing direct crashes. But the hot gas between them, that's where things got messy. Packed with protons and electrons, this superheated plasma slammed together like a cosmic traffic jam, creating a shockwave so powerful it glowed in X-rays. Astronomers expected the bulk of the cluster's mass anchored by this gas to sit right in the middle of the wreckage. But when they mapped the gravity using a trick called gravitational lensing, where massive objects bend light from background galaxies, they found something bizarre. The bulk of the mass wasn't with the gas at all. It had raced ahead, invisible and untouchable, leaving the visible matter in the dust. That discrepancy was the smoking gun. The mass had to be something that didn't interact with light or gas, something that felt gravity but ignored everything else. Dark matter. The Bullet Cluster proved it wasn't just a theoretical placeholder, it was real, making up over 80% of the cluster's mass. Think of it like a car crash where the passengers' galaxies and the seats' gas are sent flying, but the bulk of the car's weight, dark matter, phases straight through the wreckage untouched. This discovery rewrote the rules. Before the Bullet Cluster, skeptics argued that dark matter might just be a flaw in our equations, that perhaps gravity behaved differently on cosmic scales. But here, in the debris of this collision, was irrefutable evidence. Dark matter wasn't a mathematical crutch. It was a physical substance shaping the universe while remaining utterly invisible. The implications ripple across cosmology. Dark matter's gravitational scaffolding guides how galaxies form, how clusters evolve, and even how the universe expands. Without it, galaxies would fly apart and the cosmos as we know it wouldn't exist. Yet the bullet cluster's legacy isn't just about proof, it's about mystery. We still don't know what dark matter is. Is it a sea of undiscovered particles, a shadow universe interwoven with our own? Every new collision we study, every lensing map we create brings us closer to answers. And somewhere out there, another cosmic crash is waiting, one that might finally crack dark matter's code. Until then, the bullet cluster stands as a cosmic landmark, a collision that didn't just reshape galaxies but our very understanding of the universe's hidden skeleton. A fiery dance of destruction and rebirth is unfolding right now in the constellation Corvus, where two spiral galaxies known as the Antennae, officially NGC 4038 and NGC 4039, are locked in a cosmic embrace that began 300 million years ago. Seen through even a backyard telescope, their long, streaming tails of stars and gas stretch across the sky like celestial antennae, giving these colliding giants their nickname. But zoom in closer and you'll witness a stellar nursery of staggering proportions, thousands of newborn star clusters, some weighing as much as 1 million suns, blazing with the light of young, blue-hot stars. What makes the Antennae galaxies so extraordinary isn't just their inevitable merger. It's the frenzied pace of creation they've unleashed. When these two spirals first grazed each other, their mutual gravity triggered shockwaves that compressed vast clouds of hydrogen gas, igniting fireworks of star formation. Hubble's sharp eye has revealed over 1,000 of these superstar clusters, each packing more stellar firepower than most galaxies' entire globular clusters. Some are less than 10 million years old infants by cosmic standards, and their ultraviolet radiation sets surrounding gas aglow in ethereal pinks and blues. Yet this beauty is born from violence. The galaxy's original structures are already unrecognizable, their spiral arms shredded into those iconic tidal tails, streamers of stars flung into space like sparks from a grinding wheel. Within these tails, astronomers have spotted orphaned star clusters drifting away from the chaos that birthed them. Meanwhile, the galaxy's cores, now just 30,000 light-years apart, are racing toward a final collision that will see them merge into a single, chaotic elliptical galaxy in another 400 million years. For amateur astronomers, the antennae offer a rare glimpse into our own galactic future. Located a relatively close 45 million light-years away, they're bright enough to spot with modest equipment, their distorted shapes visible even in small telescopes under dark skies. Photographers revel in capturing their intricate filaments, while more advanced observers can hunt for hints of those superstar clusters' tiny, gritty knots of light swimming in the galactic haze. But the real lesson of the antennae lies deeper. These colliding giants prove that destruction and creation are inseparable forces. Every star cluster born in this maelstrom is built from gas clouds crushed by the very violence tearing the galaxies apart. The same tidal forces that fling stars into the void also compress the nurseries where new generations ignite. It's a cycle as old as the universe itself, one that shaped our Milky Way's past and will define its future when Andromeda comes calling. So the next time you peer at the antennae, remember, you're not just seeing a collision, you're witnessing the universe's endless rhythm of endings and beginnings written in starlight. Somewhere in the constellation Coma Berenices, two spiral galaxies are caught in a celestial tug of war so violent it has stretched them into cosmic mice. Officially catalogued as NGC 4676 and NGC 4676A, but better known as the Mice Galaxies, these colliding spirals are slinging colossal streams of stars' tidal tails over 300,000 light-years long across the void. Through the Hubble Space Telescope's lens, the mice look like they're holding hands, their warped disks interwoven with glowing filaments of gas and dust as gravity reshapes them into something entirely new. What makes the mice so special isn't just their dramatic tales, it's the starburst fireworks lighting up their cores. When galaxies collide, their gas clouds don't just pass by peacefully. They slam together, compressing under unimaginable pressure until they reach a breaking point and ignite. In the mice, this process has birthed hundreds of superstar clusters, each one a nursery for thousands of young, blue-white stars burning at temperatures that make our sun look like a candle. Infrared observations from the Spitzer Space Telescope reveal hidden nurseries veiled in dust, where stars are forming at rates 10 times faster than in our Milky Way. But here's the twist: these starbursts are both a beginning and an ending. The same collisions that trigger this frenzy also drain the galaxies of the gas needed to fuel future star birth. Over millions of years, the mice will exhaust their reservoirs, their brilliant clusters fading as the last massive stars explode as supernovae. Eventually, all that will remain is a quiet elliptical galaxy, a smudge of aging stars where two vibrant spirals once danced. The mice also offer a rare case study in galactic timing. Unlike the antennae, which are mid-collision, or the Milky Way and Andromeda, which are still approaching, the mice are caught in the moment just after their first close pass. Their long tails, packed with stars ripped from their original orbits, act as cosmic stopwatches, letting astronomers reconstruct the collision's history. By modeling the tail's trajectories, scientists have calculated that the galaxies first grazed each other around 160 million years ago and will merge completely in another 400 million. For backyard astronomers, the mice are a challenging but rewarding target. Located 300 million light-years away, they appear as a faint, elongated smudge in larger amateur telescopes. But their real magic lies in knowing what you're seeing: two galaxies caught in the act of rewriting their destinies, their long tails tracing the invisible hand of gravity itself. Every starry stream, every nascent cluster is a reminder that even in the vastness of space, nothing evolves in isolation. Collisions like these aren't accidents, they're the universe's way of reinventing itself, one galactic embrace at a time. Drifting alone through the cosmic deep, 300 million light-years away in Draco the Dragon, lies a celestial oddity, a galaxy stretched into the shape of a tadpole, its long tail flicking through the void like a cosmic afterthought. Officially known as UGC 10214 but nicknamed the Tadpole Galaxy, this stunning swirl of stars tells the story of a violent encounter frozen in time. Unlike the slow-motion mergers of spiral galaxies, the tadpole's fate was shaped by a hit-and-run, an ancient collision where a smaller intruder galaxy punched through its disk, then vanished, leaving behind a gravitational wound that never fully healed. The evidence is written in starlight. Hubble's sharp eye reveals the tadpole's tail, a staggering 280,000 light-years long, thrice the diameter of our Milky Way, composed of blue star clusters and glowing gas ripped from the galaxy's main body. These aren't just scattered debris, they're stellar orphans, entire generations of stars born from the chaos of the collision. When the intruder galaxy sideswiped the tadpole hundreds of millions of years ago, its gravity acted like a cosmic plow, scooping out vast streams of gas and flinging them into intergalactic space. As these ejected clouds collapsed under their own weight, they ignited new stars, turning the tail into a glittering ribbon of sapphire fire. But the real tragedy lies in what was lost. The intruder galaxy, likely a dwarf 1/10 the tadpole's size, didn't just steal gas, it stole the future. Spiral galaxies like the tadpole rely on their gas reservoirs to form new stars. With much of it now trailing in that long tail, the main galaxy's star-forming days are numbered. Infrared observations confirm this. While the tail blazes with young stars, the tadpole's core grows quiet, its remaining gas pockets sparse and depleted. Given enough time, the tadpole will fade into a dull elliptical galaxy, its once vibrant spiral arms dissolved into a featureless haze. What's fascinating is how common this carnage might be. Galactic collisions aren't always the slow mergers of equals. Sometimes they're brutal, one-sided affairs where larger galaxies cannibalize smaller neighbors. The tadpole's tail mirrors the streams seen around our own Milky Way, remnants of dwarf galaxies torn apart by our galaxy's gravity. Even the Magellanic Clouds, our Milky Way satellite galaxies, are leaking gas in a similar Magellanic stream, hinting at their eventual destruction. Yet there's beauty in this destruction. The tadpole's tail isn't just a scar, it's a stellar arc carrying the ingredients for thousands of future planetary systems. Some of its star clusters may one day break free, becoming rogue island universes drifting through the void. And in a way, the collision preserved the tadpole's story in a form we can read across the ages, a cosmic fossil showing how even the smallest crashes can leave the largest marks. So the next time you feel insignificant under the night sky, remember the tadpole. Its twisted shape is proof that in the grand tapestry of the universe, no galaxy evolves alone. Every spiral, every dwarf, every glittering swarm of stars is shaped by collisions, some creative, some destructive, but all part of the same endless dance of reinvention. In the vast expanse of the universe, some collisions leave behind works of art, none more striking than the Cartwheel Galaxy. Floating 500 million light-years away in the constellation Sculptor, this galaxy looks like it's been shot through with a cosmic bullet, its perfect rings spreading outward like ripples in a pond. But this isn't just a pretty pattern, it's the aftermath of a head-on collision so precise it turned a normal spiral galaxy into a celestial bullseye. The story begins with two galaxies, one, a typical spiral similar to our Milky Way, and the other, a smaller intruder likely a third its size. Millions of years ago, the smaller galaxy shot straight through the larger one's core like an arrow. The impact didn't just scatter stars, it sent shockwaves racing outward at hundreds of thousands of miles per hour, compressing the galaxy's gas into concentric waves. As these waves expanded, they triggered a fireworks display of star formation, igniting bright blue clusters along each ring. Hubble's images reveal these newborn stars lighting up the galaxy's outer rim like a necklace of sapphires, while the inner rings glow with the reddish hue of older stellar populations. But the Cartwheel's magic lies in its rarity. Most galactic collisions are messy, chaotic affairs, spirals twisted beyond recognition or merged into shapeless blobs. For a bullseye like this to form, everything had to be just right. The angle of impact dead center, the speed high enough to create clean shockwaves, but not so fast it tore the galaxy apart. Even the intruder's size played a role, too small, and it wouldn't have left a mark, too large, and the cartwheel would have been shredded. The aftermath tells a deeper story. As the shockwaves traveled outward, they didn't just birth stars, they redistributed the galaxy's entire ecosystem. The innermost ring, closest to the impact site, is now a frenzy of star formation, while the outer rings host older stars flung from the center. Meanwhile, the intruder galaxy, its job done, has long since sailed away, leaving only gravitational fingerprints behind. What's truly astonishing is how temporary this beauty is. The cartwheel's perfect rings won't last. Over the next few 100 million years, the ripples will fade as gravity smooths out the chaos, and the galaxy will settle into a new shape, perhaps a lenticular galaxy, a hybrid between a spiral and an elliptical. Already, observations from the James Webb Space Telescope show tendrils of gas stretching between the rings, the first signs of the structure softening. For astronomers, the cartwheel is more than a curiosity. It's a time lapse of how galaxies evolve under extreme conditions, a laboratory for studying how collisions redistribute matter and ignite stellar nurseries. And for us, it's a reminder that even in the vast, impersonal cosmos, there's room for artistry, a fleeting masterpiece painted in starlight and shockwaves. Most galaxies spin like elegant dinner plates, their stars and gas swirling in orderly disks. But then there's Mayol's object, a cosmic oddity where the rules don't apply. Floating 500 million light-years away in Ursa Major, This peculiar galaxy sports a dazzling ring of stars, gas, and dust spinning perpendicular to its main disk, like a wheel wrapped around a frisbee. This isn't just a random quirk. It's the scar of a collision so precisely angled it defied the odds, creating one of the rarest galactic structures in the universe, a polar ring galaxy. The story of Mayol's object reads like a cosmic game of billiards. Billions of years ago, a smaller galaxy, likely a gas-rich dwarf, sliced through a larger spiral galaxy at nearly a 90-degree angle to its disk. Most galactic collisions happen at messy, oblique angles, leaving their victims twisted and distorted. But this intruder hit with surgical precision, its momentum and trajectory perfectly aligned to send a tidal wave of stolen gas and stars into orbit around the larger galaxy's poles. Over millennia, gravity did the rest, shepherding that debris into the striking ring we see today. Hubble's observations reveal the ring star forming frenzied clusters of young, blue stars lighting up its circumference like pearls on a cosmic necklace. Meanwhile, the original galaxy's older, yellower stars still spin in their original disk, creating a surreal double-decker structure where two generations of stars orbit at right angles to each other. Infrared data from the Spitzer Space Telescope shows even more hidden drama. Vast lanes of dust weaving through the ring, evidence of the chaotic forces that shaped it. What makes Mayol's object truly special isn't just its beauty, it's the clues it holds about dark matter. The ring's motion betrays the gravitational pull of invisible mass shaping its orbit. By mapping how stars and gas move within the ring, astronomers have reconstructed the galaxy's dark matter halo, an invisible scaffold that extends far beyond its visible stars. Oddly, this halo isn't spherical, as most models predict, but squashed like a pumpkin, likely reshaped by the same collision that birthed the ring. Polar ring galaxies are vanishingly rare, only a few dozen confirmed examples exist, and each one is a time capsule of collision physics. Some, like Mayol's object, may eventually settle into normal spirals as the ring disperses or merges with the main galaxy. Others might see their rings collapse inward, sparking bursts of star formation in the core. But for now, they stand as cosmic reminders that even in the chaos of collisions, there's precision, a fleeting symmetry carved by gravity's exacting hand. So next time you see a galaxy spinning predictably in a textbook, remember Mayol's object. Its dizzying dance proves the universe has a flair for the dramatic, turning even the most violent crashes into works of art where destruction doesn't just distort but reinvents. On September 14, 2015, at 5:51 in the morning Eastern Time, a ripple passed through Earth so subtle it stretched the entire planet by less than the width of a proton, and yet this faint shiver marked one of the greatest discoveries in modern astronomy. The Laser Interferometer Gravitational Wave Observatory, or LIGO, had just detected gravitational waves from JWST a collision between two black holes 1.3 billion light-years away. This wasn't just a milestone, it was the opening of an entirely new window on the universe, letting us hear the cosmos for the first time. The event itself was almost unimaginably violent. Two black holes, one about 29 times the mass of our Sun and the other 36, had been locked in a death spiral for millennia, orbiting each other hundreds of times per second as they inched closer. In their final moments, they reached nearly half the speed of light, warping spacetime so fiercely that the energy released momentarily outshone every star in the observable universe combined. Then, in a fraction of a second, they merged into a single 62 solar mass black hole with the leftover mass, 3 times our Sun's, converted into gravitational waves that raced across the cosmos. LIGO detection of these waves was a triumph of engineering bordering on magic. Twin observatories in Louisiana and Washington, separated by 3,000 kilometers, each house laser beams traveling down 4-kilometer-long vacuum tubes. When gravitational waves pass through, they stretch one arm of the L-shaped detector while squeezing the other, shifting the laser's interference patterns by distances smaller than a proton. The fact that both facilities registered the same ripple within milliseconds ruled out any earthly disturbance, confirming Einstein's century-old prediction that spacetime itself could vibrate. What JW150914 revealed was just as groundbreaking as its detection. Before this, astronomers had only found black holes up to 20 solar masses, but here were monsters nearly twice that size, suggesting black holes could grow far larger than we'd imagined. Even more puzzling was how these black holes found each other. Were they born together in a binary star system, or did they meet later in a dense stellar cluster? The signal's characteristics hinted at minimal spin, supporting the first idea, but the debate rages on. Perhaps most thrilling is what this collision taught us about the universe's hidden symphony. Before LIGO, black hole mergers were theoretical curiosities. Now we know their common LIGO and its European counterpart, Virgo, have since detected dozens, including one involving a black hole swallowing a neutron star. Each event peels back another layer of mystery, from how black holes pair up to how often they form in the cosmic wild. And this is just the beginning. Future detectors, like the space-based LISA mission, will listen for collisions between supermassive black holes, while next-gen ground observatories could catch whispers from the very first black holes born after the Big Bang. JW150914 didn't just confirm a theory, it launched a new era of astronomy where spacetime itself is the messenger. So the next time you feel solid ground beneath your feet, remember, the universe is trembling with secrets and we've only just learned to listen. For most of human history, the birth of gold was a mystery. Then, on August 17, 2017, the universe handed us an answer written in gravity, light, and fire. That day, detectors in Louisiana, Washington, and Italy caught the faintest tremor in spacetime, a ripple that had traveled 130 million years from a cataclysm in the galaxy NGC 4993. But this wasn't just another black hole collision. For the first time ever, gravitational waves came with a flash, a kilonova, the explosive aftermath of two neutron stars smashing together at nearly light speed, and the key to one of cosmology's greatest puzzles, where heavy elements like gold, platinum, and uranium come from. Neutron stars are the universe's ultimate pressure cookers, corpses of massive stars so dense that a teaspoon of their material would weigh 1 billion tons on Earth. When two of these ultra-dense objects spiraled into each other, the collision didn't just shake space-time, it forged elements in quantities that defied imagination. For decades, scientists had theorized that such mergers could be cosmic foundries, but JW170817 proved it. Telescopes around the world, from Hubble to Fermi, caught the aftermath, a purple-blue fireball fading to red as it expanded, its light laced with the spectral fingerprints of freshly minted lanthanides and precious metals. Calculations suggest this single event produced over 10 times the Earth's mass in gold alone, flinging it into space where it could someday seed new planets. The data was even richer than hoped. Gamma-ray telescopes detected a short burst of radiation just 2 seconds after the gravitational waves arrived, proof that neutron star collisions power mysterious gamma-ray bursts, some of the brightest explosions since the Big Bang. Meanwhile, radio and X-ray observatories tracked the expanding debris cloud for months, watching as it smeared into a relativistic jet of particles moving at 99.9% light speed. This wasn't just a light show, it was a Rosetta Stone for high-energy astrophysics, linking 3 phenomena: gravitational waves, gamma bursts, and kilonovae into a single, unified story. But the real magic lay in the collaboration. Over 70 observatories across 7 continents and space joined the effort, from amateur astronomers measuring the kilonova's fading glow to neutrino detectors hunting for elusive particles. This marked the dawn of multi-messenger astronomy, where gravitational waves, light, and even potential neutrino signals combine to paint a fuller picture of cosmic events. Suddenly, we weren't just watching the universe, we were sensing it in every way possible. Yet JW170817 left mysteries too. The merged object, whether a hypermassive neutron star or a newborn black hole, defied immediate classification. And the kilonova's brightness hinted at physics beyond our models, suggesting neutron star material might be even stranger than we thought. Each new collision since has added pieces to the puzzle, revealing how common these events are and how much they shape the chemical makeup of galaxies. Every gold ring, every platinum necklace, even the uranium-fueling nuclear reactors, they all carry echoes of neutron stars that died in fiery embraces billions of years ago. JW170817 didn't just solve an old riddle, it rewrote our origin story, proving that humanity and everything we cherish is quite literally stardust forged in the most violent furnaces imaginable. And somewhere out there, another pair of neutron stars is spiraling toward collision, ready to seed the cosmos anew. Somewhere in the depths of intergalactic space, an invisible force is bending the universe's very fabric, a gravitational mystery so colossal it's dragging entire galaxies, including our own Milky Way, toward it at over 14 million miles per hour. Astronomers call it the Great Attractor, and its existence rewrites our understanding of cosmic motion. Hidden behind the dense stars and dust of our galaxy's disk, this enigmatic region in the constellation Centaurus exerts a pull so immense that thousands of galaxies are caught in its flow, like leaves caught in a river's current toward some unseen waterfall. For decades, the Great Attractor defied explanation. X-ray and radio telescopes piercing through the Milky Way's obscuring veil revealed a staggering concentration of mass, a knot of galaxy clusters collectively named the Norma Cluster, centered around a supermassive black hole. But here's the twist, even this gargantuan structure isn't nearly massive enough to account for the observed gravitational tug. The Great Attractor's true source must lie beyond, in something even more unimaginable. Current theories point to an ancient collision of unfathomable scale. One leading idea suggests the Great Attractor is the aftermath of a long-ago pileup of galaxy clusters, a cosmic traffic jam where dozens of clusters, each containing hundreds of galaxies, smashed together over billions of years. As they merged, their combined gravity created a density so extreme it now bends the paths of galaxies millions of light-years away. Supporting this, infrared surveys have uncovered a sprawling supercluster dubbed Laniakea Hawaiian for immeasurable heaven, centered on the Great Attractor, with tendrils of galaxies flowing into it like rivers into a whirlpool. Yet there's another, even more mind-bending possibility. The Great Attractor might not be the final destination at all. Recent observations hint that something far larger lurks behind it. The Shapley supercluster, a behemoth 8 times more massive than Laniakea, lying 650 million light-years away. Like a series of cosmic dominoes, Shapley could be pulling the Great Attractor, which in turn pulls us, a chain reaction of gravity sculpted by collisions billions of years in the making. The implications are staggering. If true, the Great Attractor isn't just a singular anomaly. It's a waypoint in a vast, invisible web of dark matter and galaxy clusters, a testament to how collisions on the grandest scale shape the universe's architecture. Every galaxy caught in its flow, ours included, is riding a current set in motion by ancient crashes we're only beginning to map. What's certain is this: the Great Attractor reminds us that even the mightiest structures in the cosmos are not static. They're dynamic, evolving, and above all, shaped by collisions past, present, and future. Stretching across over 1.4 billion light-years of space, the Sloan Great Wall isn't just a structure. It's a cosmic titan, a filament of galaxies so vast it defies the very limits of what we thought possible. Discovered in 2003 by the Sloan Digital Sky Survey, This colossal chain of superclusters, walls, and voids resembles a spider's web spun on a universal scale, with galaxies strung along filaments like beads on an invisible thread. But what makes this megastructure truly astonishing isn't just its size. It's the fact that it shouldn't exist at all, at least not according to our best models of dark energy and cosmic expansion. The Sloan Great Wall is more than a random clustering of galaxies. It's a snapshot of the universe's skeleton, a visible trace of the dark matter scaffolding that guides how matter assembles across the cosmos. Imagine pouring water onto a pane of glass and watching it gather along microscopic scratches. The water is ordinary matter. The scratches are dark matter's gravitational pull, and the resulting patterns are the walls and filaments we see. Within this structure, galaxies aren't static dots but dynamic actors, drawn together by gravity in a slow-motion collision that's been unfolding for billions of years. At its heart, superclusters like the Hercules Corona Borealis Great Wall are galactic metropolises, each containing thousands of galaxies bound in a gravitational dance that will eventually merge into something even larger. Yet the Sloan Great Wall poses a profound problem for cosmology. According to the Standard Model, dark energy, the mysterious force accelerating the universe's expansion, should have prevented matter from clumping on such a scale. The larger a structure, the more dark energy ought to tear it apart before gravity can fully assemble it. Yet here it is, a filament stretching across nearly a tenth of the observable universe, its existence suggesting either flaws in our understanding of dark energy or that we've stumbled upon something even stranger, a relic of primordial quantum fluctuations frozen in time, magnified to cosmic proportions. This collision in progress also reshapes how we think about our place in the cosmos. Our Milky Way sits within Laniakea, a supercluster that's itself a tiny thread in the Sloan Great Wall's tapestry. Every galaxy we see, every cluster we map, is part of this intricate web, a web that's still evolving, still collapsing under its own gravity, still writing the next chapter in the story of cosmic structure. Telescopes like Euclid and the Vera C. Rubin Observatory are now hunting for even larger filaments, probing whether the Sloan Great Wall is an outlier or a sign of deeper, unseen patterns in the universe's architecture. What's clear is that the Sloan Great Wall isn't just a curiosity, it's a challenge, a cosmic puzzle demanding we rethink the forces shaping existence itself. As we peer deeper into its structure, we're not just mapping galaxies, we're reading the universe's autobiography, written in the collisions we can see and the dark energy we're still struggling to understand. In the vast cosmic web where galaxies cluster like cities linked by highways, there's a place that defies the rules, a yawning chasm of nothingness so vast it could swallow thousands of Milky Ways without a trace. The Boötes Void, a spherical desert of space spanning 330 million light-years, is one of the universe's greatest enigmas. While most regions of the cosmos teem with galaxies, this void holds just a handful, scattered like lone travelers in an endless wasteland. Astronomers call it the Great Nothing, but its emptiness might not be accidental. Some believe it's the scar of a collision so catastrophic it cleared the area like a cosmic broom, or worse, the footprint of something from beyond our universe. Theories about the Boötes Void range from the plausible to the spine-tingling. One leading idea suggests it's the aftermath of a collision between galaxy clusters so violent it created a gravitational cascade, flinging galaxies outward like debris from an explosion. Picture two massive clusters smashing together, their combined gravity slingshotting galaxies into the surrounding cosmos, leaving behind a near-empty bubble. Supporting this, observations reveal the few galaxies inside the void are mostly old and red stars that formed early and have since burned out, as if the region's gas for new star birth was stripped away long ago. But there's a twist that pushes into speculative territory. Quantum fluctuations from the Big Bang could have left behind primordial voids, regions where dark energy dominated early, preventing matter from clumping. If dark energy acted like an anti-gravity force in these zones, it might have pushed galaxies apart faster than gravity could pull them together, leaving behind a barren expanse. Simulations of cosmic structure formation show such voids can arise naturally, but none as vast or empty as Boötes. Then comes the most mind-bending hypothesis. The Boötes void could be evidence of a collision with a parallel universe. In some multiverse theories, bubble universes float in a higher dimensional space, occasionally brushing against each other. If one grazed our universe, the interaction might have popped a region of space-time, siphoning matter and energy into another reality. While there's no direct evidence for this, the void's sheer scale and abrupt edges make it a tantalizing candidate for such an exotic event. What makes the Boötes void truly unsettling is how it challenges our cosmic expectations. Voids are normal, but one this large should be statistically impossible in our current model of the universe. Yet there it sits, a gaping hole in the sky, forcing us to question whether we're missing a fundamental piece of the puzzle, a hidden force, an unaccounted-for collision, or perhaps something even stranger lurking in the dark. For now, the void keeps its secrets, but every galaxy that drifts through its expanse, every radio telescope trained on its emptiness, brings us closer to understanding whether this is a cosmic accident, a gravitational ghost town, or something far more extraordinary. One thing's certain, in a universe built on collisions, even emptiness tells a story. Deep in the heart of the Ophiuchus constellation, a sleeping giant awoke with a roar so violent it shook the cosmos, an explosion so powerful it makes supernovae look like firecrackers. In 2016, astronomers studying the Ophiuchus supercluster stumbled upon something impossible: a cavity in the hot intergalactic gas spanning 1.5 million light-years, as if some unseen hand had punched a hole through the fabric of space itself. This wasn't just an empty region, it was the scar of the largest explosion since the Big Bang, unleashed by a collision between supermassive black holes with an energy output 5 times greater than the previous record holder. The numbers defy comprehension. The eruption released enough energy to power every star in the Milky Way for billions of years, blasting through galaxy clusters like a cosmic tsunami. At its heart lay a pair of supermassive black holes, one from the central galaxy of the Ophiuchus supercluster, the other from a smaller galaxy it had cannibalized. As these monsters spiraled toward each other, their collision didn't just create gravitational waves, it triggered a cataclysm in the surrounding gas. The smaller black hole, like a bullet fired into water, sent shockwaves rippling outward at nearly the speed of light, heating the gas to millions of degrees and carving out that staggering cavity. What's truly terrifying is how long it took us to notice. The eruption occurred roughly 240 million years ago, so distant that its light only reached Earth recently, and so subtle that initial X-ray observations missed its scale entirely. It wasn't until radio telescopes combined data with NASA's Chandra X-ray Observatory that the full picture emerged. Here was an explosion that had traveled thousands of galaxies, its shockwaves still echoing across intergalactic space like a pebble dropped in a pond the size of a universe. Yet the most fascinating detail isn't the violence, it's the silence. Unlike active galactic nuclei that spew continuous jets of radiation, this eruption was a single, catastrophic blast, suggesting black hole mergers might have explosive phases we've never before detected. Some theorists even speculate that such collisions could briefly switch off a black hole's feeding mechanism, creating a delayed but unimaginably powerful release of pent-up energy. For astronomers, the Ophiuchus eruption is a wake-up call. If something this colossal could hide in plain sight, what else are we missing? Future telescopes like the Square Kilometre Array will scan the skies for similar cavities, hunting the ghosts of black hole collisions past. And as we piece together these cosmic detonations, we're rewriting the story of how the universe's largest structures evolve, not just through slow gravitational tugging, but in sudden, earth-shattering bursts that reshape entire corners of creation. The Ophiuchus supercluster didn't just witness an explosion, it survived a cosmic earthquake, and its scars are teaching us how the universe rebuilds after devastation. Imagine trying to map a city's streets at night, not by the glow of streetlights, but by tracing the paths of invisible cars. That's the challenge astronomers face when studying dark matter, the universe's ghostly scaffolding that outweighs visible matter 5 to 1. But when galaxies collide, they leave behind cosmic breadcrumbs, vast, swirling streams of dark matter stretching across millions of light years. Remnants of ancient crashes that let us chart the invisible. These streams are born from violence. When two galaxies merge, their stars and gas might collide directly, but their dark matter halos, those massive, diffuse clouds of unseen particles surrounding each galaxy, pass through each other like phantom ships. Gravity distorts their shapes, stretching them into long, looping tendrils that linger for billions of years. Unlike stars, which scatter predictably in tidal tails, dark matter behaves like an invisible ink, revealing its presence only by how it bends the light of background galaxies, an effect called weak gravitational lensing. One of the clearest examples wraps around our own Milky Way. The Sagittarius Stream, a ribbon of stars torn from a cannibalized dwarf galaxy, is just the visible tip of a far larger dark matter structure. By tracking the motions of these stars, astronomers have reconstructed the orbit of their progenitor galaxy, and in doing so, mapped the underlying dark matter currents that guided its destruction. Similarly, the Magellanic Stream, a vast arc of gas trailing the large and small Magellanic Clouds, hints at a dark matter wake left as these satellite galaxies orbit the Milky Way. But the real power of these streams lies in what they tell us about dark matter's nature. Some models predict dark matter should be cold, slow-moving and clumpy, forming dense subhalos within these streams. Others suggest it's warm, with faster-moving particles smoothing out the distribution. By studying how streams bend and twist, researchers can test these theories. For instance, gaps or kinks in a stream might betray the presence of invisible dark matter subhalos, while overly diffuse streams could favor warmer models. The grandest dark matter rivers flow between galaxy clusters. When titans like the Bullet Cluster collide, their dark matter sails ahead of the visible wreckage, leaving a gravitational fingerprint we can trace. These cosmic traffic jams reveal dark matter's distribution on scales no lab experiment could ever replicate. Future telescopes like the Vera-C, Rubin Observatory will hunt for fainter streams, piecing together a web of dark matter currents that could rewrite our understanding of the universe's hidden architecture. What's haunting is how much we still can't see. Every known stream might be just one thread in a vast tapestry of dark matter flows, each whispering secrets about the collisions that shaped our cosmic neighborhood. As we learn to read these invisible trails, we're not just mapping dark matter, we're uncovering the hidden history of how galaxies live, die, and merge in the endless dance of the cosmos. Tucked away in the constellation Eridanus, a patch of sky whispers secrets that defy explanation, a region so cold it chills the very afterglow of the Big Bang itself. Known as the cosmic microwave background cold spot, this anomaly in the universe's oldest light stretches over 1.8 billion light-years, a cosmic bruise where temperatures dip mysteriously below the surrounding expanse. Some call it a statistical fluke, others see something far more radical, the fingerprint of a collision with another universe, a scar left by realities brushing against each other in dimensions beyond our own. The cosmic microwave background, or CMB, is the oldest snapshot we have, the faint glow of the universe when it was just 380,000 years old, stretched by expansion into microwaves we detect today. Normally, this afterglow is remarkably uniform, with tiny fluctuations representing the seeds of future galaxies, but the cold spot isn't just another ripple. It's a staggering 70 microkelvin colder than its surroundings, a deviation so extreme it has less than a 1 in 200 chance of occurring randomly. One explanation points to a cosmic void, a vast, empty region where galaxies are eerily scarce. If such a void lay between us and the cold spot, the light passing through it might lose energy as the universe expands, cooling the CMB in that direction. Yet surveys have found no void large enough to account for the anomaly. The few galaxies mapped in the area don't align with the scale of the cooling, leaving scientists scratching their heads. That's where the multiverse theory ignites imaginations. In some models of inflation, the universe's explosive early growth bubble universes could exist alongside ours, each with different physical constants. If one of these bubbles grazed our universe in the distant past, the collision might have drained energy from that patch of spacetime, leaving behind a colder imprint in the CMB. It's a speculative idea, but simulations show such an encounter could create a disk-like cold region remarkably similar to what we observe. Skeptics counter with less exotic solutions. Perhaps the cold spot is an artifact of foreground interference, dust in our own galaxy distorting the signal. Or maybe it's evidence of a rare cosmic texture, a defect in spacetime structure left over from the universe's birth. The Planck satellite's detailed CMB maps ruled out some instrumental errors, but the debate rages on. What makes the cold spot so tantalizing is its audacity. Either it's a fluke so improbable it challenges our understanding of statistics, or it's a window into realms beyond our own, a cosmic what-if written in microwaves. Future telescopes like the Simons Observatory aim to study it with unprecedented precision, hunting for telltale patterns in polarization or temperature gradients that could tip the scales toward one theory or another. Until then, the cold spot remains a riddle wrapped in the universe's oldest light, a reminder that even in our most refined maps of reality, there are still shadows where the unknown lingers. Whether it's a quirk of physics or the first evidence of a multiverse, one thing's certain: the cosmos still holds mysteries that refuse to fit neatly into our equations. Every story must have an ending, even the universe's. After billions of years of cosmic collisions shaping galaxies, forging stars, and birthing elements, the final act won't be a whisper but a cataclysm. The fate of everything hinges on a battle between two invisible titans: gravity, the relentless pull that binds matter together, and dark energy, the mysterious force ripping space apart. Depending on who wins, the universe's finale could be a crushing collapse, a violent shredding, or a slow, silent fade, each scenario rewriting the rules of reality itself. Let's start with the most cinematic ending, the Big Crunch. Picture dark energy weakening over time, its repulsive grip faltering until gravity finally takes charge. Galaxies, drawn together by an unstoppable tug, begin merging in a cosmic pileup. At first, its orderly clusters like Laniakea coalesce into supergiant structures, their collisions igniting brief eras of new star formation. But as space contracts, the sky transforms. Distant galaxies once receding from view now loom larger, their light blue-shifted as they barrel toward us. The temperature of the universe rises, the cosmic microwave background warming from frosty microwaves to visible light, then X-rays. In the final moments, every atom, every black hole, every shred of spacetime is compressed into a singularity, a mirror image of the Big Bang, where the universe's entire history collapses into a fiery dot. Some theories even suggest this singularity could rebound, birthing a new universe in an endless cycle of collisions and rebirths. Then there's the Big Rip, a far more violent farewell. Here, dark energy doesn't just win, it escalates, growing stronger until its expansion overwhelms everything. First, galaxy clusters are torn apart, their gravitational bonds no match for the stretching spacetime between them. Then individual galaxies unravel, stars ripped from their orbits and flung into the void. In the last hour, planetary systems disintegrate. Earth, or whatever remains of it, is shredded as dark energy overcomes the forces holding molecules together. Even atoms aren't safe. Nanoseconds before the end, nuclei are torn apart, then quarks, until reality dissolves into a sea of disconnected particles too far apart to ever interact again. The universe doesn't just end, it's vaporized, but perhaps the most chilling finale is heat death, not a collision, but the absence of one. Dark energy keeps expanding the universe, but at a steady pace. Galaxies drift beyond each other's horizons, their light fading from view. Stars burn out, black holes evaporate via Hawking radiation, and matter itself decays into radiation over unimaginable eons. The temperature of the universe approaches absolute zero, and all movement ceases. No collisions, no energy gradients, just an eternal, uniform silence. In this scenario, the last remnants of civilization might huddle around the dying embers of a black hole, counting down the trillions of years until even it winks out. Yet there's a wild card: vacuum decay. Imagine if the Higgs field, the quantum backdrop giving particles their mass, isn't in its true lowest energy state. A random quantum fluctuation could trigger a bubble of true vacuum expanding at light speed, rewriting physics as it goes. Fundamental constants like the speed of light or the strength of gravity could change instantly, making stars, planets, and life impossible. This collision with a new set of physical laws wouldn't just end the universe, it would replace it. What's haunting is that these scenarios aren't just speculation, we're already gathering clues. The accelerating expansion of the universe favors dark energy's dominance, making heat death the current frontrunner, but mysteries linger. If dark energy's strength varies over time, as some theories suggest, any of these endings could still be in play. Future telescopes like the Euclid mission aim to measure dark energy's influence with unprecedented precision, potentially ruling out certain fates. No matter how it ends, the universe's final act will be shaped by the same forces that built it: collisions, expansions, and the endless tug of war between order and chaos. Every galaxy we see, every atom in our bodies, is a temporary structure in a cosmic drama with no curtain call. So when you look up at the night sky, remember, you're not just stargazing. You're witnessing a story still being written, one collision at a time. From the unimaginable fury of the Big Bang to the delicate dance of colliding galaxies, every atom, every star, and every life form in existence owes its existence to cosmic violence. Those 25 collisions we've explored weren't just accidents, they were the universe's way of building, recycling, and reinventing itself. Without them, there'd be no oxygen in your lungs, no iron in your blood, no gold in your jewelry. Even the device you're watching this on contains silicon forged in the heart of dying stars, then scattered across space by supernova and neutron star mergers. The universe didn't create life gently, it hammered it into existence through cataclysms of unimaginable scale. Take our own solar system as the ultimate example. The giant impact that birthed the moon didn't just give us tides and lunar eclipses, it stabilized Earth's tilt, creating the seasons that drive ecosystems. The late heavy bombardment, chaotic as it was, might have delivered the water that fills our oceans. Even the gold in your wedding ring was likely forged in a neutron star collision billions of years ago, ejected into space and eventually swept up by our young planet. Every piece of our world is stitched together from the debris of cosmic collisions, each one a thread in the tapestry of existence, and this story isn't over. Right now, the Milky Way and Andromeda are racing toward each other, destined to merge in a fiery embrace that will reshape our galaxy forever. Supermassive black holes spiral toward collisions that will shake spacetime itself. Neutron stars, silent and dead, are drifting toward mergers that will unleash gamma-ray bursts and forge new heavy elements. The universe isn't done building, it's just getting started. So the next time you look up at the night sky, remember, you're not just seeing stars, you're witnessing the aftermath of billions of years of cosmic violence, the wreckage of collisions that built everything from the ground up. It's a reminder that destruction and creation are two sides of the same coin, that chaos doesn't just tear down, it rebuilds. We are stardust, yes, but we are also the children of catastrophe, born from the wreckage of the universe's most spectacular crashes. And if that doesn't make you pause in awe, nothing